Okay.
Now we finish after at 2 o'clock. The first.
Yeah, you finish when you feel, and then I'll stop the record.
Okay.
Okay, you just sit and enjoy yourself.
Yeah, thank you very much.
Okay, we are here basically people from the two courses, both the field development operation and the gas. I'm not sure who is who, and of course, on the paper we are 4 times bigger than what we see here in the class, but I think it's a very nice opportunity for you to meet someone with slightly different background. And we invited Mahmoud Etermaddar. Okay. He took his PhD in the Marine Department here. He's a naval architect by education, work on reliability issues. If you have time, maybe he'll tell you what he's done in his PhD. And he works in Sivan Marine, IS, which is the company that deal with offshore platforms, offshore engineering. And the flagship now in Norway is the Goliath field in north of Norway, in the Barents Sea, which is kind of a round-shaped structure. And yesterday we said a few words, the advantage of having something that looked like a kayak with a turret in the center compared to something which is a round shape, so it doesn't have to rotate all the time to get minimum wind. But he prepared it, and in fact the arena is his. Learning to know the architecture of the field is part of our course. We didn't decide yet in which way we'll ask you to capture what he presenting here in terms of exercise. Either it will be design and architecture of the field or something of that nature. But I think first we have to go through that. You ask any question you want. He planned to have coffee break in 2, but in fact, if we can go the first 2 hours at 1 and then take a break. But you decide whenever, okay?
That's okay for me.
These people are tolerant, and, but they'll not go more than 1.5 hours at once.
Right.
Because once you stop, I have to go and stop the record.
All right, yes.
So please, and we're very happy to have you and start the sitting like me, not very lectures in it, and you sit as they present. Many people just write on the board with the back to the class, so he is here, and it's a great pleasure for us to have you. Please.
Thank you. So, hello everybody and good afternoon. I'm Mahmoud Etermaddar, a senior naval architect from company offshore oil company called Sevan Marine AS. It's a Norwegian company. Head office is in Arendal, and we have offices in different cities, and I'm located in Oslo office. So this is my pleasure here to give this presentation for you on this topic, concept selection for deep water field development planning. The main goal of this presentation is to give you or to introduce a methodology for concept selection for offshore deep water field development. In this regard, first I make an overview of offshore oil field development planning process, and then I will explain main stakeholders in this area, what are the main decision drivers for field development planning and especially concept selection, which information and data to be generated during field development planning, what is the source of uncertainty and how we handle them, and which part of this information should be used for concept selection. And then I will give a structured concept selection methodology, which is quite used these days at offshore oil engineering or offshore operator oil companies, which will be followed by an example and questions. But whenever you have a question, just raise up your hands and stop me. I can answer your question during the presentation. So based on the initial schedule of the class, I have divided this presentation into 3 different parts. First part is deep water field development planning, which I think most of you are quite familiar with that. It's mainly about subsurface. And then second part is a concept selection process, and third part is an example. But let me see why I selected this topic, or why I, as a naval architect, became interested in topics. Because first of all, this topic was one of my personal concerns, both during my education at the university and also during my career at industry. And also this topic was not touched upon properly during my education. at least at Department of Offshore Engineering, and I haven't seen any courses in any university yet on this topic. And also this is one of the main challenges for all of the offshore oil operators. And also it's a very interesting topic because it's an interdisciplinary topic, and when you study this topic, you will be familiar with other disciplines in your business. But what should you expect from this lecture? Definitely you will be familiar with concept selection process for deep water offshore oil and gas fields, and this presentation is only an introduction to this topic. So you should not expect to be a field development planner after this lecture, and you will definitely need much more information and much more experience. Classification of offshore oil and gas fields. To reduce the effort to select proper technology and to select proper strategy and cost estimation method suitable your offshore oil and gas field, it is better first to categorize offshore oil and gas fields based on major properties. So in general, we can classify offshore oil and gas fields based on these main characteristics: water depth, environmental condition, and reservoir size. For example, based on water depth, with the main function of operation, not drilling, because then the classification would be different. For operation, we can classify deep water offshore oil and gas fields, or better to say offshore oil and gas fields, to shallow water, intermediate water, deep water, and ultra deep water for this range of water depth. But these are not fixed definition. This is just rough estimation because the industry is improving, because up to now the technology which have been used for shallow water, which is jacket, have been used to the maximum water depth of 420 meters, which is a Bullwinkle jacket in Gulf of Mexico, I think. And this is approved technology for this water depth. The other parameter is environmental condition, which is characterized by two main parameters: significant wave height, which is the characteristic wave height, and wind speed. And we can divide environment or offshore oil and gas field based on the environment to harsh environment, moderate environment, and benign environment. And when you are going to the harsh environment like Northern North Sea, you know that definitely you cannot use FPSO with a sprit mooring system. So then you need less effort to select your concept. Or based on reservoir size, we can define them to marginal reservoirs, medium-sized reservoirs, large reservoirs, or sometimes I've seen ultra-large reservoirs as well, which is based on the reserves in the reservoir. And also we can divide offshore oil and gas field based on hydrocarbon type. It can be oil reservoir, gas reservoir, or oil and gas reservoirs. And also it can be categorized based on the pressure and temperature: low pressure, low temperature; medium pressure, medium temperature; and high pressure, high temperature. But you may have this big question in your mind: why we should go to deep water when we have a significant amount of onshore and even shallow water offshore oil and gas resources? The answer can be explained by this graph here. This is the global energy demand based on historical records for last 45 years and forecasted for next 15 years. As you can see, global energy demand is still increasing, and oil and gas still make a major contribution to that. On the other hand, if you look at the historical offshore, shallow water offshore, onshore and deep water offshore production during last 50 years, which is shown here, the bottom part shows the onshore oil production, light blue shows shallow water oil production, and this black one shows deep water offshore oil production. By looking at this graph, you can figure out that onshore oil production has passed the peak in 1979 and is declining in different parts of the world with the average rate of 4 to 8% per year. And also shallow water offshore production is almost unchanged, or even some records show that it is also declining. And what remains is only deep water offshore, which has a 9% contribution to the total oil production, and this production has to be increased to 35% to cover global energy demand in 2030. So what remains is, that means what remains is only deepwater offshore oil and gas resources. But operation and planning for deepwater offshore is quite different from shallow water and onshore oil and gas production. As you can see here, deepwater offshore oil and gas exploration and production is more challenging. But what makes it more challenging compared to onshore and shallow water offshore? Fortunately, the technology for deepwater explorations and production up to 3,000 meters have been developed and approved. That means now human is producing oil and gas into water depth of 3,000 meters. But what still makes this business different from onshore and shallow water offshore is, first of all, you need higher capital cost, drilling cost, and exploration cost. There is high uncertainty in most of commercial parameters like well performance and recovery and oil prices, and there is substantial risk for operation in this area. As you can see here, a small failure in the system can lead to such a big consequences, and you may lose all of your property there. Because you are working in remote area, maybe 200 miles from onshore, you are working in harsh environment like west of Shetland, like northwest of Australia, and most of the time you are working with high pressure, high temperature reservoirs. Yes, please.
How this well performance is related to the depth of the sea?
Yeah, because as far as I know, in deep water measurement is more difficult than shallow water. And then when you have a less accurate measurement, then this will directly affect your prediction. And also we had less analogy in deep waters, because one of the things that help us to figure out the characteristics of our new field is the analogy. For example, you have a similar field nearby, you have been producing for several years from that, you can use that information. But we don't have such an amount of information yet for deep water.
Can I interfere?
Please, yes.
In order to know the well performance, it's a highly non-linear, the rate of the well versus the downward pressure. So you have to make really a multi-rate test. And each rate might take 12 hours. 12 hours in a deep water rig costs $500,000. You come to the management and say, I want to make 4 rates tests, because without it, I really don't know what's going on. If I have 1 point, I can put, and say, no, $500,000 to test your well, it's enough. Then you make 1 rate. In shallow water, it costs 1/4. You do 4 rates, you do 14 rates, and then you know much more about your well at initial stage. It's the multi-rate test that really they can't afford because of the rig time that it takes to do the test. It's not the instrument is less accurate, it's how many procedures you can do in deep water, how much time you get to play with, how much is the budget. Go ahead.
Thank you very much. So now we'll make some fundamental questions to be considered during this presentation, and we are actually going to answer these questions. 1, when should concept selection process be started during field development planning? What is the required information to be used for concept selection? How we should make decision based on the available information? And finally, who are participating in the concept selection process? To better understand the position of concept selection during field development planning, you should note that concept selection is a subset of multidisciplinary process called field development planning. As you probably know, typical offshore oil and gas life cycle can be divided into 8 subsequent phases, which start with acquiring the lease, which usually government, based on the size of the block and location of the block, they make a bidding process. Different operators, maybe alone or group together, will attend this bidding process, and one or group of them will win this exploration license, and then exploration, which is the first phase, will start. That operators with geological study, exploration methods, exploration technology, they will specify the first location for wildcat drilling. And the main objective is to find the reservoir. And after you find the reservoir, you start another phase, the third phase, which is appraisal, which is not actually start exactly after exploration, because some of the activity you will do parallel with exploration activities. And the main objective is to specify or to improve your information about the dimension of the field, field life, field characteristics, production rate, and reserves. And after you have enough information, you can go to concept selection phase. That you specify different concepts, and then you do technical feasibility, economical viability, you calculate the revenue, required investment, and there is one important point here to notice. When you are doing concept selection, there is a still high uncertainty in the reservoir characteristics.
Can I make one comment?
Yes.
You see this green, this is a very touchy, because at that point, you have to decide whether you keep the well at the field and go and develop it, you commit yourself for developing, or you give it back to the government. As we say in English, relinquish it to the government. So there is a big decision point here. You have to issue a statement of commerciality and then plan for development operation. Now, one of the things that you are here in doubt, will you make more appraisal before you decide what to do? Because do you drill 2 more wells to get more information, or you are happy with these 2 wells that you have discovered? So these 2 parts here are playing a very, very major role. All the rest is technical work, but here someone has to decide to keep it, and then I commit myself to the government to develop it and produce it for another 25 years, or I give it back immediately. That's that. Okay?
Yes, thank you very much. So after selection phase is engineering phase or feed phase, that you do some engineering work on your selected concept to prepare all the required documents for next phase, which is execution, which consists of procurements of the raw materials or equipments, construction of the unit, transportation, installation. And when you have your unit ready at the site, you go to the operation phase, which consists of commissioning and startup, and the rest of job is operation and maintenance and taking care of safety. And after field life finish or production rate drops below economic margin, we go to the last phase, which is abandonment, which you may need to remove the infrastructure completely there to avoid any damage to the environment, or you should plan for reuse it to make some commercial from that. For example, you can use the available structure for neighboring fields, which have been discovered later. But why field development planning became so important in offshore oil industry, and especially in deepwater offshore oil industry? To answer this question, we can take a look at the historical development in offshore oil industry, which was mainly or initiated from Gulf of Mexico. So first floating production unit in Gulf of Mexico have been used in 1986, which was Green Canyon 29, which was a semi-submersible. And after that, just during 13 years, 12 floating production units were sanctioned, which were SPAR type, semi-submersible, and TLP type by major oil operators, big operators. But after that, just in 2 years, boom in using floating production unit happened. And 14 floating production units have been used in Gulf of Mexico just in 2 years, consisting 11 dry tree and 3 wet trees. And this time, independent oil companies, smaller oil companies came to the game. So then you can imagine that how big competition were between them. And during 2000 to 2005, even with the low oil price, 13 floating production units were sanctioned in Gulf of Mexico, 10 dry tree and 3 wet trees. But what was the reason for this acceleration? The reason was, one, high oil price for oil and gas for some period, which shows that there is a potential for production from deep water. And also lack of oil and gas for United States and United Kingdom during 1970s that forced them to become independent on hydrocarbon reservoirs and try to explore their own reservoirs. And also relatively low upstream capital cost at that time. So this makes high competition for acquire the new leases and increasing the production between different operators But this, which have very bad consequences, this move the operators towards faster and cheaper solutions.
What is this dry tree and wet tree?
This is type of the Christmas tree, which I will explain later. Depends on the position. If you have a Christmas tree on the seabed, we call it wet tree, and if it is on the platform, we call it dry tree. I will explain this later. But this had very bad consequence for our industry, which discovered few years later. An assessment of existing project in 2005 by major oil operators shows that a significant percentage of deepwater offshore oil and gas reserves were underperformed both technically and commercially due to poorly executed field development planning. That was not mainly due to weakness in the execution or technology. That was because they have selected wrong concept. For example, after few years of operation, they realized that they need 4 more risers on their platform, but they haven't considered enough space there. So this fact has been explained with this beautiful graph here. This graph shows that in first 4.5 phases of offshore oil and gas field, that you can have the major influence on the value of your project if you have a poor definition. I mean, if you don't spend enough time and enough money, and you don't have poor definition. In execution phase, if you have a good execution or poor execution, there will not be so big difference. But if you spend enough time and money here and you make a good definition on your project and good planning, during execution phase, even if you have bad execution, poor execution, you still get much more value compared to first case. So now let's see what is the objective of field development planning. If you consider this green area here as a field development plan, and this red area are major players and main decision drivers. The main objective of field development planning is the selection of the plan that satisfies operators' commercial, strategic, and risk objectives subjected to regional and site constraints. Or in a simple word, the main objective of field development plan is to maximize the revenue for given investment, which is characterized by this single quantity utility index. But in order to have successful field development plan, you need a continuous and effective collaboration and alignment among main stakeholders, which are, or the main key players, which are subsurface team, which are actually you guys, drilling and completion team, surface facility team, commercial team, operation and maintenance team. And weak communication between these key elements in early years of offshore oil and gas industry was the main reason of underperformance. In fact, all of these teams were working independently without considering the effect of their results on the subsequent discipline. This flowchart here shows a methodology for concept selection. If we start from the top, in the first step, subsurface team makes a initial reservoir model based on seismic data, well logs and well tests and other measurements. And after that, subsurface team together with drilling and completion team makes different depletion scenario for the reservoir, based including different well counts, different top hole locations and resulted production profile. And their main objective is optimizing drilling program. That means greatest recovery with fewest well. But why number of well is very important for deep water? Because drilling and completion may be something around 25% or even up to 50% of total budget required for field development, while this can be much less in onshore or shallow water offshore. In the next step, surface facility team will identify different or basic building blocks based on this depletion scenario and they will consider site conditions, existing infrastructure, and market strategy, and they will generate multiple development scenarios for this field, which is called concept screening phase. But in this step, you may end up with several, even up to 80 different concepts, which is difficult to compare them accurately. Therefore, in this step, you make first stage screening, and you make mainly qualitative comparison to reduce your number of concepts to 5, 10, let's say 5, 10 different concepts. And in the next step, which is called concept selection, subsurface facility team together with economic and risk management team will consider different production term conditions, commercial matrices, strategic drivers, reservoir uncertainty management methods, and they will make a quantitative comparison, more accurate comparison between the remaining concepts until they finalize one concept, which will be sent to the selection phase. So this is the whole story of concept selection and screening in one slide. But who are the or what are the main input parameters and their effect for field development and concept selection? In general, we can divide the parameters into 6 different groups, including reservoir geometry and geology, which has the greatest effect because they can directly determine recovery factor and flow rates, well count, location and construction, secondary recovery methods, then fluid properties, which can directly affect the subsea and topside design, operation and maintenance requirement, drilling and completion, which can directly determine the well management requirements and well intervention frequency during production. After that, regional and site constraint and regulations, site characteristic and operator strategy, which we will explain in more detail in following slides. So this is just, for example, shows the relative importance of parameters, reservoir geology and geometry. Usually field development planners keep this as a main guideline in their mind, and they know that permeability is very important, for example, for secondary recovery. So this is one of the quantities should be characterized as more accurate as possible, and almost there is no limit on that. You should try to improve your understanding about the probability, the permeability as much as possible. Or this is the effect of other parameters on the key field development components. Or for example, this slide shows the relative importance of fluid characteristics or their effects on field development components. This is just to show how important are different parameters for field development planning. Now we will take a look at the responsibility of different teams during field development planning and mainly concept selection. The first team is subsurface characterization team. Their main objective is to characterize the reservoir, but how reservoir is defined. As you can see here, an oil and gas reservoir is characterized when you determine these parameters. First, you should determine the geometry, areal extent, dimension, and connectivity of the reservoirs. You need to specify rock properties, including lithology, porosity, and permeability. You need to determine hydrocarbon type and saturations, oil and water and oil and gas contact lines, fluid physical properties, fluid systems and chemical compositions, driving mechanisms of the reservoirs, flow rate and pressure variation over time. When you specify these parameters, then you can have a reservoir ready for concept selection.
Can I make a comment?
Yes,
You're going to have a copy of the slides presentation.
Definitely, yes.
You're going to have it on It's Learning, a copy of the slides. So you don't have to capture by writing every word, but you take a note for yourself.
Yes,
You're going to
yes.
have.
Yes, thank you very much. So as we showed earlier, the first step after acquiring the lease is exploration. The main goal of exploration is to find an economic oil and gas reservoirs. The main task of this team is first to specify the suitable location for exploration drilling and require total depth. And main activity is wildcat drilling, and after you get into the reservoirs, you can do a step-out drilling and do some measurements. But in many places, even this strategy, which is the old strategy in onshore oil and gas exploration, is not cost-effective because the cost of drilling is too high, and then you cannot just drill one well here, and after you find the reservoir, you cannot make a step-out drilling 4 wells in 4 directions. It can be too expensive. And then exploration team, including geologists, geophysicists, drilling engineer, reservoir engineer, and mud loggers, will use different exploration methods, which we can start from methods with good horizontal resolutions like satellite survey, gravimetry, magnetometry, and seismic measurements, which give you good horizontal resolutions. And then you can also improve vertical resolutions by exploration drillings, measurement while drilling, logging while drilling, core sampling, and well testing, and collect required information to make your reservoir model. And then at the end of this step, you make the initial reservoir model prepared for development, including reservoir geometry, rock properties, fluid characteristics, and so on, as we explained before. But now there is a big question at, yes, please?
What's the meaning of vertical and horizontal resolution?
Yes, because when you want to characterize your reservoirs, you should make like a 3D, at the end you want to make a 3D model of that. These methods which we shown here, satellite survey, gravimetry, magnetometry, seismic, they give you good resolution in horizontal direction. So then you can just understand what is the characteristic of this layer and this layer, but you cannot understand what is the what is the difference between these 2 layers and how reservoir rock properties is varying between these 2 layers. And because of that, you should use, the only method can help you is drilling. You make drilling in some points, and then you do some measurements while drilling, and then you put all of this information together in a reservoir model software, and then you get a full 3D picture of your reservoir. But at the end of exploration step, your boss may ask you a big question. Is it an economic oil and gas reservoir? And you can tell him you should spend $10 to $100 million more to answer this question. Because there is still substantial uncertainty in the measurements and reservoir information even after you find reservoir. And because of that, to improve our information, we start another phase, which is called appraisal phase. The main goal in this phase is improving the quality of the data and reducing uncertainty. The outcome of this phase will be well fluid characteristic, original oil in place, recoverable oil production profile, but still with sufficient uncertainty. Uncertainty actually is your best friend during field development. You cannot completely remove it. And in this phase, the method which you are using is quite similar to the method you have been using during exploration. For example, you make more appraisal wells at some different locations, but with more measurement, or better to say, much more accurate measurements. In this step, Subsurface team finally will provide robust reservoir model for you from seismic data, appraisal wells, and well logging and well tests. And in this step, one of the main tools is reservoir simulation, as you can see here, which you will do some multiple simulations with varying well type. You have some measurements during appraisal phase, and then you start making some new wells with your reservoir simulation software, and you try to fit your data in your software to measurements. And using that, you can characterize uncertainty in your parameters. The uncertainty is defined by a general function called probability density function. That this probability density function tells you what is the probability of each numbers you have here in the x-axis, and probability of occurrence of this function is shown here. And finally, at the end of appraisal phase, you should provide production profile and pressure depletion curve, which will be used for concept selection. But for field appraisal phase, there are several different methods. There are several methods and strategies to reduce uncertainty that is shown here. And there is always a trade-off between cost and risk reduction. If you need more accurate method, you should spend more time and more money. And different methods which are available now is drill steam test, more appraisal wells, extended well test method, early production, and stage development and phase development strategy. It's not actually only a method, it's some strategy. For example, instead of developing field completely, you divide the field to several phases, like Johan Varstrup now, and then you start production in one phase. After you collect some more information and improve your understanding about the field characteristics after 5 years of production, you make a new planning for the rest of the field. So application of this method depends on the reservoir size and characteristics, operator strategy, and available technology. So here, just for example, we have a table which shows these different strategies and methods, their general descriptions, their typical durations of the test or method, and advantage and disadvantage, and some examples that you can take a look at it later. It's quite self-explained. So here, to just show the complexity of the problem, we make a glance to the mathematical, basic mathematics of the field development. For example, original oil in place is function of several different parameters, as you can see here. And all of these parameters are in somehow stochastic time varying parameters. They are stochastic and they are also varying over time, some of them. Or here, for example, is oil production rate. Again, it's function of several different parameters like downhole pressure, reservoir pressure, permeability, which are also, some of them are a stochastic problem. And you can, for example, specify production rate by curve fitting to the well test data and fit your measurements to exponential, harmonic, and hyperbolic data. Or after some years of operation that you have enough information available, you can make a sophisticated reservoir simulations, and by energy balance method, you can improve your reservoir estimation and production rate. But as you can see up to now, it is very difficult to make a decision based on multivariable stochastic problem. But we should find some way to integrate all of these uncertainty together to a single problem and then make a decision on that. As suggested by the Society of Petroleum Engineering, for financial evaluation, uncertainty in all the parameters should be integrated into the single parameter, which is production profile. And then at the end, you can have 3 different confidence level for your reserve estimation, or for your production profile, better to say, which are known as proven, probable, and possible. Just to understand those, it's better to say if you make a calculation based on the information which you are 90% sure about the correctness of the data, you will get proven. You will get one profile. If you just use the data which you are 50% sure about that, it will be probable. And if you make an estimation based on the data which are 10% you believe that they are correct, you will get possible. And you will get 3 different curves. But there is no guarantee which one is correct at the end. And this is the operator's decision or strategy to make the plan based on that. So field development should be based on one of these 3 values here, and this depends on the operator strategy and commercial risk of the operators. But typically, planning is based on probable or 50%. But some part of the design, for example, when you plan for the main process train, you plan it for 50%. But when you are planning for the available space for risers, you plan it for 10%. So the next team is drilling, completion, and well intervention team. So well construction and intervention is the main objective of this team. But what does well construction mean? Well construction actually means determining construction of the well in the first place, which includes specifying the location of the wells, which can be either production well, water injection well, or gas injection well, required depth of the well, direction of the well, and well casing design. And also determining well type, which can be production well, water injection well, gas injection well, and also type of completion, including perforation zone. I mean, which part of the well you have to perforate to start production from that part, and with which sequence, because level of the oil and gas is changing during the field life, and to have optimum production, you should find the best location of the perforation zone and how to change it during production life. And also perforation method can also directly affect well performance, for example, sand production. And also one of the main decisions which affect concept selection is type of access to the well. Whether you need to have a direct vertical access to the well, I mean from your floating production platform, or you can have a non-direct vertical access. You can have your floating production platform here, and you can have access like this. Which well construction will have a direct effect on productivity and frequency of well intervention. Well intervention and workover is some services you have to give to your well during production. You have different options. You can have a workover package or workover unit on your floating production unit together, or you can have workover and drilling services on a separated platform on mobile offshore drilling unit or on a drill ship. This is also one of the decisions you have to make during field development. And typical workover and well intervention system services we have, if we just sort them from heavy service to light service, are casing repair, recompletion, replacement of downhole boosting pump, or logging after production. For example, when you start production from your well, you may get some sand production, which depends on both on rock properties, reservoir rock properties, and also it can depend on type of completion. And this sand production may reduce your production, and then you have to stop production, send some equipment inside the well, clean up, and then start production again. Or you need to reperforate some new zones because the oil level has been changed. Or even your estimation was wrong, and after some production by reservoir simulation, you understand this was not the optimum zone for production. You have to move it to new places. And also, as we mentioned, one of the main decisions in during well construction and well intervention is type of completion, or better to say, type of well and well access, which depends on the location of Christmas tree. You have in general two options. You may have subsea well, which is also known as wet tree with direct vertical access or non-direct vertical access, both are possible, or surface well, or dry tree, which only direct vertical access is possible. This is an example of dry tree system, which is exactly the same technology which we are using in onshore. And this is wet tree system, which is the Christmas tree with some additional equipments for automations and also for safety, as you can see here, which is located on the seabed. But why we should use wet tree for some reservoirs and dry tree for some other one? Because of the advantage and disadvantage of both. Wet tree or subsea well, as you can see in these two pictures here, have in general lower capital cost but higher operation cost. That this depends on the number of wells and also operators' strategy, which put more emphasis on capex or opex. And also in general, subsea well give you lower recovery compared to dry tree. This is not absolute recovery. This is just 5 to 10% less than similar dry tree system. And also it's usually suitable for low pressure reservoirs, but it gives you greater flexibility for well placement. As you can see here, you can just put your wellhead whenever you like. And then you can just have a direct drilling, and you don't need any directional drilling, which can increases the cost of drilling significantly. And also it's suitable for high uncertainty reservoirs and multiple sub-economic reservoir development. And also all host units support wetry, then you don't have any limitations for top of floating production unit. And also both direct vertical axis and non-direct vertical axis are possible.
So why the recovery is less in this case?
One of the factors at least which I know is because of technology which you are using on the subsea system, which you need more safety there.
Can I say
yes,
something?
sure.
Maybe you look an analogy to a dentist. You come to a dentist sitting in a building of 14th floor, okay, and one dentist, one clinic. You sit on the chair and the dentist fixes your teeth, and he can fix it until you are 90 years old. Fix all the time one teeth. In the next two, there is a dentist that sits on the 14th floor. You sit on the chair on the first one, and he just manipulate the thing and the tooth from this long distance. Now, of course, he'll do if there's some problem, the one that sits in the 14th floor, and fix your mouth. If something wrong a little bit, he'll pull the tooth, because that's the easiest to do from the 14th floor. It's exactly the same analogy. You can really play with the tooth until you're almost dead if he sits next to you. But if he's in the 14th floor and you have to deal with it, something wrong, let's pull it up. And basically that's what happened with the subsea. There's no, the variety of tool and operation that you can do to maintain perforation have been plugged, you have to squeeze them and open another zone of the perforation. The cement is not good, there's communications, water start to come, you want to have to make hole and insulation, you have to change function. All these things that you can do, a big toolbox of operation that you can do in a well if you stand next to it. You cannot do when you are 1,200 meters below. It's just expensive, you just pull the tooth, shut in the well, finish, go home. Okay?
Yes.
Remember the dentist.
But on the other hand, dry tree or surface well needs higher capital cost but lower operation cost. So if you have a reservoir with like 25 years lifetime, so maybe dry tree system can be better because it has a lower operation cost, and accumulation cost in the long term will be much less than wet tree system. And also it has in relatively higher recovery. It's suitable for high pressure reservoirs, which is also very important. But you can only use it on fixed platform or floating production platform, which has very limited horizontal motion, like a TLP you can see here. And only direct vertical access is possible. As you can see, the dry tree system requires direct access to the well and top tension riser. And also you have a limitation for type of risers, which are these flue lines from seabed to the platform. But one of the advantages is that you can put full drilling package on floating production unit, which also can, for big fields or for large reservoirs, it can significantly reduce the total cost of the project. And the requirement for for complete drilling package in Gulf of Mexico depends on the size of the reservoirs and number of wells. When you have very large, for example, most of the reservoirs with the reserves more than 170 million barrel of oil equivalent and more than 12 wells have full drilling package on floating production unit. And the reason is that you can leave some of the wells to be drilled completely and completed after operations. And also you can do all the workover and well intervention services from your floating production unit. But selection of wet tree or dry tree depends mainly on areal extent and complexity of the reservoirs. So if you have a small and compact reservoir, then surface tree with central well cluster, I mean you just drill all the wells from one point with directional drilling technology, can be a good option or first priority. But if you have a stacked, highly faulted and aerially extended reservoirs, like the figure you can see on the right side, then wet tree system with satellite well system and tie back to the floating production unit can be a better solution. But beside these three themes, there are also some main decision drivers for field development planning. One of them is regional considerations or regional parameters, which have a significant effect on net present value and net present investment, and also field development process, such as block size, infrastructure, market influence, local contents, regulations, contract terms and conditions with host country, and sustainable development. For example, when you go to Gulf of Mexico, most of the blocks are in the size of 10 to 15 square miles. Then it gives a potential for independent oil operator companies like Maersk Oil, like VNG Norge, like Lundin, to come to the bidding process. But when you go to the west of Africa, you see most of the average block size is around 200, 230 square miles. So then it makes it difficult for independent oil operator, and usually major oil operators or small oil operators have to be grouped together and share the risk to each other and attend the bidding process, which can consequently affect the strategy, because the strategy of the operators highly depend on the size of the operator companies. Or when you are developing a new field, you should also take a look at the available pipeline, because if you know, for example, in North Sea, you are not allowed to flare the gas, and you have to export the gas. And if you are far from the available gas network, then it can be one of the major costs in your project. Or some other parameters, just you can take a look at it later. And also another decision driver is site conditions, which directly affect field architecture and floating platform, such as water depth. Water depth, for example, there is a one-to-one relation between the water depth and drilling cost. This, because it can directly affect design and installation of the risers and mooring system and pipeline. And also when you increase water depth, the temperature of the seabed, water at the seabed is reducing, which can make some flow assurance issue for you, for pipeline and flow line design. And also bathymetry and geometry, for example, can directly affect subsea flow line installation cost and anchor design. Meta-ocean condition, which can affect installation window, which is very important parameter for concept selection, because, for example, when you go to the North Sea, and during winter time, you have very limited suitable weather window for installation and for repair, for example. Then, when you are in the concept selection phase, it can be one of the decision parameter for you, because you will not go towards the concepts which needs long offshore installation, like a spar. So then this might be also one of the reasons that you don't have so much spar and TLP in North Sea. And also remoteness, how far you are from coastline, which can increase the cost and risk of installation, and favor the concepts with minimized offshore installation and operation. And this data should be provided prior to undertaking the facility development plan. Otherwise, your concept selection would be not so reliable. But also, as we mentioned, operator strategy is very important decision parameters, which can be related mainly to the size of oil operator companies. Oil operator company in general can be divided into three main groups: independent oil companies, international oil companies, and national oil companies. And a strategy of the operator is directly related to the position of the operator towards these trade-off pairs, CapEx or OpEx. I mean, the operator emphasize or give more weight to the capital cost or operation cost. A standardization versus improvement, because usually major oil operators have some standardization strategy in their development, which limits their flexibility. And then when they are going to the concept selection, that limits them for innovative solution. Proven technology versus innovative technology, and main capacity versus future capacity. And here, independent oil companies almost operating 15% of deepwater offshore oil production. The focus of independent oil company is mainly on the small to medium-sized field because of their capital cost and the amount of risk they can take. And they usually join with other operators to share their risk. And also they prefer leasing a strategy when they are going to the production. For example, VNG Norge, they are now developing a field, Pile and Bu, and they are in the concept selection phase. But the final solution for them, which they have decided about, is FPSO. But now they have two solutions, a new build FPSO or leasing FPSO. But finally they decided to go with lease FPSO because it needs, especially in this market, it needs less capital cost and less risky for them. And also they usually have short development cycle time. And they have a small engineering team with fast tracks. They are also first user of new technologies, because usually new technologies, one of the benefits of new technologies is reducing a schedule to first oil. And this makes them more flexible towards vendors. And Subsurface is usually the largest team in their company. And confidentiality also is quite high. For example, my friends who are working in VNG Norge, when they are getting to the close to the reservoir during drilling, they are completely isolated from others, because they can, if for example you know that you are getting to the reservoir now, you can just call your friends and tell him, okay, you can buy 5,000 share of my company, and suddenly after they find the reservoir, their share will rise by, let's say, 5-6%, and you can make a lot of money. And this is why they usually have very security for exploration team. And international or integrated oil companies like BP, Shell, ExxonMobil, they are operating 50% of deepwater oil production at the moment. Their focus is on medium-sized to large-sized fields. They're usually using their own technology as long as possible. For example, now my company is designing a FPSO for Shell. Up to now, when we are designing FPSO, we also take responsibility for the topside. But now Shell told us we have our own team to design topside. So then, for this project, we only designed the floating production unit, the hull and riser and mooring system. And they have more process-driven stage gate, which increases development cycle time to first oil. For example, when we send one document to Shell for approval, it takes 2 weeks. But when we send this same document to Premier Oil, it just takes maybe 1 day or even less, because they have less stage gate approval system. And they prefer to use proven technology. Again, when we are working with Shell, Shell is very concerned about the proven technology. Even polyester rope, which is using for the mooring line, have been used for more than 10 years now. For Shell point of view, is not proven technology, because proven technology, that means something which has been used for more than 15 years. But a small oil operator, they don't care about that. Just use something that can reach us to the first oil as soon as possible. And also, standardization technology is one of the major strategies in international oil operators, and which makes them less flexible towards vendors. And finally, national oil companies, which are operating 35% of deepwater oil and gas reservoirs, which are mainly Petrobras and the Statoil, their focus is mainly on global development plan and basin development rather than just block development. And they are the user of phase development strategy and early production users to reduce uncertainty, and they can take more risk because they have higher risk margins, and exploration results even can be publicly available. For example, after some years, I don't know how many, but 5, 6 years, Statoil give free access to the exploration results, because then it will be cheaper for the other oil operator company to come here and make the exploration. Or even, I heard that, is it correct? Norway provides some exploration fund to the exploration oil companies. After they get to the reservoir, they can pay back.
New companies that come to Norway get 85%
really?
of the cost of exploration first.
Yeah.
So, but they don't have time. They have to work quick. I mean, the whole thing about exploration is 5 years. Okay. Now, some places they allow you 5 years to play and come with a concept and start to develop, and then you have another 25 years to produce. But some places they say, okay, you have 2 years, and after 2 years you have to give half of the block back to the government. So within the first 2 years, you have to do all the seismics and everything possible to decide which half you want to stay with. Then another year, they say half of the half or to give back. They want to force you not just to see it and wait to see what the other are doing, and then hopefully that some of the neighbors will do discoveries, and then you decide what to do. No, you are under. So you see here, he said this takes 6 months and that takes more months. You have no time. You have to work very, very quickly, and if you don't do that, they take the field back from you, or you make a bad decision. You declare commerciality, you commit yourself to a development, and then you get stuck because the banks don't want to give you money. They think it's not a good enough prospect. So, but in Norway, they give, it's a very strange situation because all the small companies are running here. They do exploration. They don't know how to do development. They don't have money to do development. But for the exploration, it's only 15% of the cost. The rest they pay for the government. That's the strategy here, and it works. Now, it's different in areas which are mature. Here, for example, there are certain areas in Norway that consider kind of new areas, and they say, well, you have to be crazy or very rich to go to explore. We'll help you. We'll subsidize it. But in areas which are very mature, very rarely the government give you such incentives. So Norway is a little bit special, but each country has different strategy to how they sponsor, how they subsidize the exploration of newcomers. The ones that are there, they can pay the exploration from the cost of the producing field. But the new company to enter, they don't have anything to deduct the tax, the cost against it. The government give you 85%. Hurrah.
Yes. The next team, if you feel tired, maybe we can have a break. But if not, we can just.
Have a break.
Yes, we can have a break now. Thank you very much.
You can leave it. Let me just do the recording. Staying back.
We'll come back in 15 minutes.
Okay.
Let's say 3:40.